work on our next example. This time it is going to be a network-based exploit. In our previous example, it was all local. There will be certainly local exploits if you continue in exploit development. We saw some client-side attacks when we did that section, something like Adobe Reader, music player, anything that is local privilege escalation, for instance. But these next few are going to be network-based, so like many of the exploits we used in this class, we will have something listening on the port that's vulnerable, and we will attack it over the network. So for this example, we're going to use Windows XP, and we'll have Kali as our attacker. So on XP, we actually need to make a simple change. So if we open up the XAMPP control panel, we currently have FileZilla FTP running. Let's go ahead and stop that. Open up that port 21 TCP for another FTP server. You can close that up. And now if we go to the war FTP folder, we have all our war FTP programs here. So we actually want this yellow thing that looks like part of a state, really. This is FTP, so this is the war FTPD daemon. Let's open that up. And we can click OK through the opening banner that says who wrote it. And we need to put this online. By default, it is offline, as it says down here. So we would want to hit this lightning bolt up here. So I'll go online. And sure enough, it's online, and it's listening on the IP address of XP on port 21. So what we want to do now, before we start exploiting it, is we want to, like we did with GDB in the previous example, we want to hook it up to a debugger. There are many different options, really, for debuggers in Windows. Probably the most powerful would be WinDebug or WinDBG, which is a little bit, I think, more complicated than the one we're going to use. We're going to use one that I like to use called Immunity Debugger. It is pretty powerful. It has its limitations, like we can't do any kernel debugging with it, so in that case we'd have to use WinDebug, but I like to use Immunity Debugger when I have the option, and I think it's especially nice for beginners. So let's grab Immunity Debugger. It is this red, black, and green 3-leaf clover, and it opens up this graphical window for us. And so we want to attach to war FTP, so we go to File and Attach. We have a list of our processes. So we want war FTP. It's easy to spot because it's listening on TCP port 21. So if we look at the listening column, we can see port 21 here. So we can click Attach. And we see that it attaches to the process, and it's paused at DBG breakpoint. So basically it pauses when the debugger attaches. So what we want to do is click the play button up here to tell it to continue, so the program will run so we can attack it. So now it's running. You can see that down here at the bottom right. Just going to make this CPU window bigger. So I'm just maximized it. I can make the font bigger. I typically don't, because if I make it bigger then it starts to like run off the screen. But you can make it bigger if you go to Options and Appearance. You go to Fonts, you can make it bigger. It's not much bigger really, but you can make it bigger. Like if I'm teaching in front of a class, I typically do. But you know, you can make yours bigger so you can see it on your screen since this is recorded. But you know, you do have that option if you want to teach this yourself. It's kind of worth knowing because it looks microscopic on a projector. Alright, so this is running and we are hooked up to the debugger. Again, I made this CPU window maximized, so I have 4 panes here. Go to different windows. You can go to View, up next to File, and we will see some of these other views as we work through these examples. Some of them we won't see, with the CPU window is our default here. So we have our CPU here at the top left. Top right we'll have our registers. We have EAX, ECX, EDX, EIP, and we have our dump here at the bottom left, and bottom right we have our stack. Alright, so naturally we need some sort of exploit here for war FTP. So if we pop back over to Kali, if you look at the materials that are included with the course, I do have some exploit skeletons. We don't have to know much Python for this class. We did, of course, cover a bit of Python previously in our third module. But I gave you the exploit skeleton, so this is just war FTP skell.py, and as you can see I copied it onto Kali's desktop, so you can download that file. It is included with the course. It just has the basic Python code, so we can focus on trying to build our exploit string. So I change directories to desktop and do a cat war FTP skell.py. So first we have user bin Python, so it tells it to execute in Python interpreter. We import a socket, so that's going to be a Python library. That, as the name implies, sets up a network socket. We see buffer, so a variable named buffer equals a times 1100. S equals socket.socket, blah blah blah. So that's just how you set up a socket in Python. If you're not familiar with it, you could basically just Google it, how to set up structures like this in different programming languages. Is not really something you need to memorize in your head. You can always look it up, of course. So that's probably what I did when I first wrote this. And then I tell it to connect, so s.connect. We are going to have to change this IP address to the IP address of your XP machine. So I will look up mine, of course, and yours may be different. And port 21, that is the TCP port for FTP. We print out a response if we receive one, then we send the correct syntax for giving the username to an FTP server, so it's just user space, whatever our username is, and then hit enter, so /r/n or /r/n. And our username is buffer. Remember, buffer is a times 1100. So we're basically giving it a really long username, probably much longer than the developers expected, because who would want to type in a username that long? But that's generally how exploit development goes. We give it unexpected input that the developer didn't know was coming, and possibly make the program do something strange. Again, we print a response if we receive one, and then just to finish the login, we do pass space and then the password. And obviously there is no user called a times 1100, so we just need some password, so I just gave it password. All uppercase is the password. And then we close the socket, so we just need to make it take our username and password and try and process it in order to get the vulnerability to trigger. So if you copy this onto the desktop, you may have to do a chmod plus x, of course, to make it executable. And we do need to change that IP address. So I'm going to use nano. And what is my IP address? WarFTP actually told me 192.168.1.76. Change yours to meet your environment accordingly. That is the only change we need to make right off the bat. We'll leave that a times 1100 as our attack string, as our long username. We will make changes to that as we work through this example. Again, we've got our simple source code here, so we don't have to worry about the nitty-gritty of the Python code. I encourage you to learn at least one programming language well. Python is used a lot in information security. Ruby is also used a lot. Not so much Perl. I used to write in Perl all the time, but not many people use it anymore. C is always a good one to know, but I encourage you to know a bit of lots of languages and at least a lot of one language, but you don't really have to for exploit development, honestly. Just basics is probably enough. Alright, so let's go ahead and run this. Just /warftpscale.py. We don't have to give it any arguments. We've hard-coded our IP address in. We could instead take that as an argument if we wanted to. So we get printed out to the screen our welcome banner, and it says please enter your username, which we do. And then it says username okay, need password, and if we recall, we do send over the password and then close the socket. So everything worked as expected from this side, but of course what's really interesting is hopefully what happened over here. So here we have our WarFTP and Immunity debugger where we left it. When we left it, it was running. Now if we look down here at the bottom right, it is paused. It says we got an access violation while executing 41, 41, 41, 41. Well, do we remember what 41 is in hex? We do a man ASCII. That'll tell us. So hexadecimal 41, if we've forgotten, is going to be over here in the second column. 41, big A, just like in our previous example. So we sent it 1,100 big A's. So it looks like those big A's, much like our previous example, they overwrite that saved return address. We don't know what our functions are called or anything at this point. We don't have any source code for this, but chances are we overwrote some saved return address, and when the function popped off and we tried to load that saved return address, it was overwritten by some A's, and 41, 41, 41, 41 is not mapped to the process. Again, it could be. There's no hard and fast rule that says 41, 41, 41, 41 will always make it crash. If you continue in exploit development, no doubt you will find examples where it doesn't crash. But for now it did in this example, so it tried to execute at that memory address and it crashed. We also see there seems to be a lot of 41s on our stack, and looks like we've got some 41s in some of our registers too. Looks like ESP, EBP, and EDI all have some A's in there. So in our previous example, we could just look at our debugger output and we could count, oh, we need 9 A's to get to our return address, which is 4 bytes long, so we could do A times 9 plus B times 4. We don't really have that luxury here. We don't know what A's are which. We have 1,100 of them to begin with, and we don't necessarily know that what's showing up in memory necessarily starts at A number 1. It might not. We don't really know how it's being processed. There's some sort of login functionality that's trying to check our username and password, and it crashes at some point here, so we don't really know what's going on. We could do some reverse engineering to try and figure it out, but that's more advanced. So we need some way to figure out which 4 A's those are. So traditionally, what one would do, if we go to, let's open up Notepad here so I can show it to you. Traditionally, what one would do would be break it into like A times 500 plus B times, well, 550. This is 1,100. 550 and B times 550. Restart it, send this exploit string, and if it's overwritten with 41, 41, 41, 41, we know it's in the first half, and if it's overwritten with 42, 42, 42, 42, we know it's in the second half. So say it's in the first half, then we would restart and do A times 225 plus B times 225, and then C times 550, because we know that the second part is not where it is. So then, we'd run it again, and if it was A's, we'd know it was in the first half, and if it was B's, we'd know it's in the second half, and then say it's in the first half again, we'd split that in half. So you'd slowly but surely, with lots of tedious work, narrow it down to the exact 4 bytes, which was tedious and boring, and I can't believe people did that for as long as they did. Naturally, we have a better way of doing this, so that's what we will do in the next video, is try and solve where exactly our saved return pointer overwrite happens in the attack string, as well as where exactly we have control of these registers, because they will come in handy as well. In our previous example with Linux, we just jumped to another function, but I mentioned that we're going to use shellcode here that we're going to generate with MSF Venom, the more traditional way of doing exploit development. So we'll need somewhere to put it, And it looks like controlling those registers might be a good place to start.